Hi everyone, it's my great pleasure to introduce to you today Filipe. He studied chemistry in Lisbon and did his MSc in organic and physical chemistry. He then moved to Germany to Stuttgart for a PhD in quantum chemistry. Afterwards, he joined the Linde engineering firm to study computational thermodynamics, and since 2021, he has been located at the Helmholtz Munich, where he combines his expertise in organic chemistry, theoretical chemistry, and thermodynamics to the field of structural biology and structure-based drug discovery, which he will talk about today. I've seen him speak several times, and he's an excellent speaker, so I'm very excited to hear his talk. Over to you, Philip.
Thank you very much, Jennifer. Thank you very much for everyone who joined today. So I suppose and I hope that the presentation is now being shared. As mentioned, so my name is Filipe. I'm a quantum chemist by formation, and I work now at the Institute of Structural Biology, where I do mostly computational method development for structural biology and computational biophysics applications. And today I would like to share with you some words on one of the new methods that we've been developing, the in-pocket analysis, and how it can be useful for you in your research. So, as the name more or less implies, and my background also implies, I'm a chemist. So the main focus of the talk is going to be chemistry. Why is chemistry still important? We'll start with this brief motivation. Then we will introduce the in-pocket analysis algorithm, how we devised this algorithm, what was the initial purpose. We analyzed stressed molecules. Then we go for benchmark cases. What can we do with this algorithm? What is the purpose? We have two examples, axitinib binding to the BCR-ABL kinase, and also analysis of structural models of curcumin bound to DIRC2. Finally, we'll see some downstream applications, some short stories to show some of the applications that we envision for our algorithm. And without further ado, then let's start with the presentation and motivate why chemistry is still important and perhaps even more important than ever. And for this, let's imagine that we have at our hands a simple modern task of using an AI structural model, say AlphaFold 3, to predict the structure of a known protein. The protein that I chose for this is cytoglobulin B, which you have represented here in this slide. Now, there are several experimental crystal structures of cytoglobulin B, all of them present in the PDB files that you have depicted down there. You can see the structures overlay with quite good accuracy, not only on the secondary structure, but also with the atomic detail. Now, cytoglobulin B is a special protein because it contains a heme group that you see here. You see the metal ion, the iron ion, and the porphyrin ring. And in this case, the heme group is coordinated to two histidine residues in the protein structure. The upper histidine, that is always N-coordinated in all of the structural models, and the lower histidine also always N-coordinated to the metal ion in all the structural models. So now we move to the AlphaFold predictions. What could possibly go wrong? And since this is a known protein, the structure is known for many years, it's a bit unfair to ask AlphaFold to predict something that it already knows, because most likely this was already used for training of the AI model, of this AI model. Therefore, to try to see how AlphaFold generalizes, we introduced some small peptides, 5 in total, generating 25 structures of cytoglobulin B bound to several of these peptides. And here is an overlay of 5 of the structures that we ask AlphaFold to predict. You can see that overlay or the consistency between these different models is even higher than with the experimental models. The secondary structural elements are all perfectly aligned. The atomic detail is overlaid with almost perfection. But if we look at the chemical detail, there are some things that are not so perfect. We start with a lower histidine, which in all of the 25 AlphaFold models that we predicted was N-coordinated, meaning it's chemically consistent and chemically correct. On the other hand, the upper histidine is only N-coordinated in 6 of the 25 AlphaFold 3 models, meaning, in other words, there are 19 different structural models, predicted models, where we have a C-coordinated histidine, which is basically chemically incorrect. The question that we have is, what is the underlying reason for this? That one histidine is clearly correct in all of the structural models that we predict, and we expect that if we give even more different models, that we would have similar predictions. And whereas the other histidine is incorrect in almost all of the structural models. What is the underlying reason for this? Is this the AlphaFold model is not good enough? This is highly unlikely because AlphaFold basically is behind a Nobel Prize. And we all know, we all used AlphaFold before, so it's expected that the quality of the model is good enough. Is it the underlying data? Well, a possibility, we need to check the data, we need to basically dig into the PDB and see if we find incorrectness of such level. Or is it simply the chemistry? It's too hard, it's not well annotated, and AlphaFold simply cannot predict the structures correctly. In other words, or overall, given our experiences from before, given this experience, this example that we see here, and there are other examples with transition metals where similar things happen, we know AI excels at predicting geometric features, but the chemical detail may be captured with less reliability. Now, what could have gone wrong? One of the reasons that we pointed was data in the PDB archive. We need to search for additional structures, and if you think about globins, you might think about hemoglobin. Here is a structural model of hemoglobin solved with a 1.07 angstrom resolution. Now you can detect that this is hemoglobin. We see 5 different hemogroups. Each one of these hemogroups is basically mono-coordinated in this structural model. And this already implies that there's a different chemistry going on. That dual versus mono coordination is basically reflective of different ionization states of the transition metal of iron. In the case of cytoglobin B, the iron center or the iron atom ion sits in the middle of the porphyrin ring. This is an iron ion in the oxidation state 3. In the case of hemoglobin, the iron sits slightly above the porphyrin ring, and this hides the different oxidation state of the ion of the metal ion, which in this case is basically iron 2. But if you look closer enough, you'll see that in one of the chains of this model, there is also a C-coordinated histidine that could have justified the learning of C-coordinated histidines by the AlphaFold model. Now, is this the only example that we find in the archive? No. Go to a completely different class of proteins, a phosphotriesterase, solved with a significantly lower resolution, 1.99 angstrom. In this case, we have 2 different transition metals. We have an iron center, we have a cobalt, 4 histidines, 2 of which are C-coordinated. And as a chemist, this already gives me the shivers because this is completely incorrect, okay, from a chemical viewpoint. Now, okay, we realize there are problems in the database regarding oxidation states of metal centers. Do we have other issues of chemical quality, of chemical accuracy? Let's change completely the topic, and now we tackle the problem of kinase inhibition. And for this, I chose a very specific target, BCR-ABL. This is a kinase, a non-natural kinase in the human body, because if your body starts expressing BCR-ABL, this basically means that you are suffering from chronic myelogenous leukemia. This used to be a very deadly disease. Since the year 2000, the introduction of imatinib completely changed the fate of people suffering from CML, and a deadly disease became basically chronic. Other medicines were introduced in the market, like ponatinib, to target specific mutations of BCR-ABL, and we also have another drug that can basically inhibit this kinase named axitinib. There are several structural models in the PDB that can basically corroborate this whole story and can allow us to understand how these drugs can basically bind to the kinase, inhibit it, and basically keep the disease from progressing. We're going to focus on the 2 structures of axitinib that we have depicted here. On the upper model, we can basically see that we have the unmutated form of the kinase, threonine 315. In the lower depiction, we have the isoleucine mutant, basically the T315I mutant of BCR-ABL. And we basically have the same drug bound in the same pocket in the 2 different variants. So as a quantum chemist, I like to run quantum chemical calculations. So what I did was to basically prepare the systems, add the hydrogen atoms, process the ligand, process the protein, generate a structural model that I can run calculations on. And from these calculations, we estimate the relative energetics from which we can estimate the relative enthalpy of binding or a scoring function. And for these 2 particular cases, according to what was the information deposited on the PDB, we obtain a relative enthalpy of binding of minus 23 kcal per mole, give or take. Now, I don't expect most people to have a feeling for what 1 kcal per mole means. 23 sounds to be a bit off, sounds to be a bit too much. If you compare this to the isothermal titration calorimetry experiments of the same inhibitor to 2 different mutants of the same protein, you start feeling that this value might be a bit too large, meaning that we need to use 23 kcal per mole to change a ligand from one pocket into another. And if I tell you that the hydrolysis of ATP to ADP costs something like 5 kcal per mole, we basically see that this value is completely off, because it means that we need to hydrolyze 5 molecules of ATP in order to change the ligand from one variant of the protein to another. Now we can keep on processing the data because there's IC50 values available. From these IC50s, we can estimate the relative Gibbs free energy of binding, from which we can back calculate a relative entropy of binding that we obtain the value of minus 72 calories Kelvin per mole. Again, significantly large value, doesn't seem overly realistic, and basically this implies that there's something implicitly incorrect in the structural models that we are using, or something potentially incorrect with the quantum mechanics. Now the question is, what is wrong in these models? Can we find the problem that we have in these models? And more importantly, what is the impact for structure-based drug discovery? Now, at this point, we reach some conclusions or some hypotheses that there are errors of chemical accuracy, of chemical nature in the PDB archive. This is known for several years. And the question that we have is, what's the impact for structural biology, AI modeling, and more importantly, drug discovery? Because in the end of the day, we at Helmholtz are interested in these sort of applications. And more practically, how can we spot and fix these errors? This is where we introduce then the in-pocket optimization algorithm, and we are trying to use this in a transformative way for structural biology applications. So what is the in-pocket optimization, how we devised, how we came up to this algorithm? Everything started with the analysis of deformation energies. And most of you never heard perhaps about what the deformation energy actually is. This is basically the energetic cost of taking one molecule of inhibitor from its free state in solution inside the protein's pocket. In other words, how much I need to pay in terms of energy to take the molecule in solution, to twist it, distort it, fit it inside the protein's pocket so that it can bind to its protein target. And in order to analyze deformation energies, we took one big database, the PDB-Bind database, which contains 20,000 protein ligand structures, for which we calculated then the deformation energies. These are calculated then in the way that we take the structure deposited in the PDB binds, we evaluate the energy of the structural model, which already contains the hydrogen atoms. This gives us the energetics of the bound ligand state. We then refine each and every single one of these ligands quantum mechanically and constrained optimization without the protein, and this gives us the free ligand in solution. So we have 20,000 ligands, we can get a histogram, some statistics, and this is the results that we obtain. Now we see here the distribution. This is a reasonably not so tall distribution, so to say. We have a reasonably broad peak between 10 and 20 kcal per mole. We have a reasonably slow decay that goes all the way up to 1,000 kcal per mole. Now, we already dealt a bit with kcal per mole. We saw that 20 kcal per mole can be quite a bit. 1,000 kcal per mole is a lot. How much a lot? Let's put things in perspective. 80 kcal per mole means that we have enough energy to break a carbon-carbon single bond. In other words, can we find so easily in a database of 20,000 structures one protein that can twist a ligand so much, can twist a molecule so much that we are lucky that it does not break a carbon-carbon bond? Moreover, if you check this histogram, can we find 100 of those proteins so easily in a database of 20,000 protein ligand structures? So are we looking at deformation or are we looking at something else? In order to answer this question, we basically look at the underlying data. And for this, we classified the molecules in 4 different classes. We looked first at the low deformation energy structures, which would be represented by the molecule that you have here. And the problems that we found were mostly of two types. One, we have suboptimal angular distortions between 3 heteroatoms that are seen in the experimental model. On the other hand, the crystallographic models, predominantly, they don't have hydrogen atoms. We need to add those hydrogen atoms using some algorithms. These algorithms are ambiguous, and the addition of the hydrogen atoms corresponds to basically some minimal distortions with respect to the optimal quantum mechanical state of the ligand. Therefore, this also introduces a few additional distortions. Then we look at the medium-low range of deformation energies. These basically corresponds to short clashes inside the structural model, most likely coming from proton-proton clashes. Again, because the crystallographic models are basically deposited without the hydrogen atoms because they're not experimentally observed. Then we go to the medium-high range of deformation energies, and we have a much more subtle problem at hand. The molecule that we have here represented has a deformation energy of about 50 kcal per mole. You look at the molecule and you don't see anything particularly wrong with it. But the devil lies in the detail, and the detail here is basically the nitro bond. If you look at this model, the experimentally deposited NO bond distances are 1.4 angstrom, 1.18 angstrom, and these two values are deviating quite significantly from the reference NO bond distances of about 1.26. Particularly in this case, we have a deviation of almost 0.2 angstrom. On top of this, there's another problem, that is the nitro bond, or the nitro group, is expected to be symmetric from a chemical viewpoint, and these two distances are anything but symmetric. So there's an asymmetry coming from how we solve the structural models, coming from the restraints, that is basically introducing chemical inaccuracies. And if we go to the high deformation energy domain, we'll basically find anything. And this anything can be a complete disaster, that it was involved in some sort of crash. The 6-member ring is completely distorted. The 5-member ring is broken. The sugar is split in two, and the phosphate ring is basically flat on one of the sides. So we have significant inaccuracies in the structural models. They come mostly from incomplete modeling. Incomplete from a chemical viewpoint, not from an experimental viewpoint, because the hydrogen atoms are missing. And we also have limited resolution and potentially poor practices. Now, we have problems. Let's focus on the practical side. Can we fix this? And in order to fix this, we came up with then the in-pocket optimization. What is this? We take a molecule and we assume that this molecule can basically be described by the quantum mechanical equations. So the energetics of this molecule are given by the Schrödinger equation. Now, if we optimize a molecule without any sort of restraint, we have the free molecule in solution. So we need to add a bias, and this bias has the only purpose of fixing the conformational state of the molecule while we run an unconstrained optimization in order to remove strain in the bond distances and in the bond angles. In other words, we optimize the bonds, we optimize the angles, we keep the conformational state. Now, with this algorithm at hand, we can revisit our database analysis, and we can basically change what we saw before to distortion. And we can now evaluate the deformation energy according to the new model that we're bringing forward. And the histogram that we obtain is now significantly different, and is represented here by this blue curve. What do we see? First of all, the distribution has a narrower peak at about 5 kcal per mole. 5 kcal per mole is 2 to 4 times smaller than what we had before. So we have an improvement of 2 to 4 times with respect to the original molecular distribution. Moreover, we see that the peak is also shifted to the left. There's a significantly faster decay. We don't get rid of the highly distorted molecules, but we significantly reduce the numbers. So we have an improved database in our hands. Now, this is about how in-pocket optimization came up. But deformation energies are something that are quite boring, only things for quantum chemists to worry about, because we cannot deal with such big systems. So most of you never heard about this before. How can you use this, and how can we transform basically this algorithm into something useful for the whole community? And this is where in-pocket analysis comes in place. So how does this whole thing work? We built a script that processes a protein ligand structure automatically for the user. And in this script, you basically give as input a certain ligand, the ligand of interest. In our case, we're going to revisit the case of axitinib bound to BCR-ABL. So we're going to focus on the ligand axitinib. Then we identify the ligand. The algorithm starts by searching all the residues in a certain vicinity of the ligand of interest, all the amino acids in the protein structure. And what we're going to do is then to run a series of in-pocket optimizations, so experimentally biased quantum mechanical optimizations of all the ligand residue pairs. But we don't do this for one chemical state of the ligand, meaning for protonation, tautomeric, or even conformational state of the ligand. For instance, what is deposited on the PDB. We do this for all of the chemically accessible states of the ligand inside the protein's pocket. In other words, we run a series of experimentally biased quantum mechanical optimizations for every tautomeric, protonation, and eventually conformational state of a ligand inside a protein's pocket. What do we get in result? Something that looks more or less like this. We have different chemical states of the ligand, all of them different in some sort of fashion. And then we have a list of residues, the residues in the vicinity of our ligand. And for every chemical state, we have a curve, and this curve basically gives us the ligand residue interaction energies, which is basically these ups and downs. Now, it's a bit messy, this whole data. Can we read it in a sort of quick and dirty way? Well, yes, very easy. We put a line around 0. Everything above 0 is bad. Everything below 0 is good. Why are things below 0 good? This corresponds to attractive interactions, and they basically stabilize the ligand inside the protein's pocket. Why are things above 0 bad? Well, they basically represent clashes. Clashes are not chemically, physically, or even biologically meaningful. Therefore, chemical states of the ligand with clashes, they are not biologically meaningful, and we can exclude them from further consideration. In this case, axitinib bound to BCR-ABL, we identify 1, 2, 3, 4 different chemical states that contain clashes. Therefore, we can exclude them from being biologically relevant. Interestingly enough, this is what was originally deposited in the PDB, these chemical states, and the analysis indicates something else should or must be there. So we have differences with respect to what was originally deposited from a chemical viewpoint. Now, does this make sense? We go back to the structural model, and here we have a representation of axitinib and its experimental electronic density bound to the BCR-ABL kinase. We have here the region of the hinge, and with the original PDB deposited ligand topology, we can see we need to put a hydrogen atom in this position here. This hydrogen atom is going to clash with the main chain nitrogen or amide bond from the kinase's hinge, therefore leading to a less favorable chemical state of the ligand inside the pocket. And therefore, the modification of putting the hydrogen atom in this nitrogen here is chemically meaningful. Now, I know that you don't have the full codes of the PDB down there, but you need to believe me that this structure was solved with a 2.2 angstrom resolution. And the question that I have next, particularly for the crystallographers in the room, is can we basically, at 2.2 angstrom resolution, distinguish the orientation of the terminal pyridyl ring? And in other words, do we have the pyridyl ring as we have depicted here, or can we flip it by 180 degrees because nitrogen and carbon cannot be distinguished and have a completely equivalent or not a chemical state, conformational state of the ligand inside the pockets? You can look at how the ligand fits the experimental densities. For a non-expert, both of the rings fit equally well at electronic density. So now we have an algorithm to test and see whether we reach some improvement. So we can basically flip the pyridyl ring, 180-degree flip. We rerun the in-pocket analysis, and we obtain the light green curve that you see here. And if you pay close attention, you see that light green curve is always below the dark green curve. In other words, the interactions between chemical state 6 and the protein are better, are more favorable than the interactions between chemical state 5 and the protein. So we might have a better representation of the ligand inside the pocket. But both chemical representations, they lead to only stable interactions. Therefore, it's a fair question to ask, what do we have there in the pocket? Do we have only one chemical state 6, because it's more favorable, or do we have an equilibrium between these two different chemical states? And with this analysis that we have here, we cannot answer, so we need additional metrics. This additional metric we can basically obtain by summing all the ligand residue interaction energies. We add additional things like the formation energy, the relative energy of the tautomeric states, so on and so forth, and we reach an in-pocket binding energy. Now, it's important to state that this in-pocket binding energy is not a binding energy per se, because we miss cooperative effects, but it's instead a metric of model fitness. How good is this representation of the ligand inside the protein's pocket? We can now use this metric to compare chemical state 5 with chemical state 6. We see a difference of 22 kcal per mole. We saw before 22 kcal per mole is a lot. Therefore, we conclude chemical state 5 is not reasonable inside this protein's pocket. We can now go back to the model and ask the question, why? And it's obvious, because if we have something like this, the original conformational state of the ligand, we have a soft clash with this main chain oxygen from the kinase's hinge, and we're missing a hydrogen atom. If we flip the pyridyl, we get rid of this soft clash, we make a hydrogen bond with the nearby tyrosine 253. So overall, what changed in the chemical representation of the ligand? Well, first and foremost, we need to change the position of the hydrogen atom. This is a very small change that is not sensitive in most of the traditional crystallographic metrics. And then we need to flip the pyridyl ring. In both cases, these two modifications get rid of clashes and establish new interactions with the protein. So I hope I was able to convince you guys with this example that InPocket can effectively analyze chemistry in a pocket. Not only points towards problems, it suggests fixes, and we can have a potentially better protein ligand binding interface. Now, is this everything that we can do? Let's see in another example, and the next example corresponds to curcumin, a small molecule bound to another kinase, DIRC2. Now, I selected two different PDB structures here, the 5' and the 6'. These analyses can also be done using different chains within the same model. So the question that we're trying to answer is, we have different structural models of one protein ligand complex. Can we say whether one model is better than the other? And this is a very interesting case, because if you zoom into the binding pockets, you'll realize that the binding mode of curcumin differs quite significantly in the two models. So here we have a structural depiction, and you can see that in both cases, the way this D-keto group of curcumin engages with the kinase is completely different. In the case of the 5' models, the D-keto group, the two oxygen atoms, turn away from the hinge and towards the solvent. And in the case of the 6' models, the two oxygen atoms engage directly with the hinge and are opposite from the solvent. And on top of this, there's also a different isomeric states. In the 5' model, we have a trans and a cis double bond. In the case of the 6', we have trans-trans. So we have completely different representations of the ligand inside the pocket, completely different binding interfaces. And the question is, which model is right? Are both right? Is one preferred over the other? What is the situation that we have here at hand? So we can start the in-pocket analysis. In this case, curcumin is a completely different case from what we had in axitinib, because the chemistry is significantly more complex. We start with two keton groups that have keto-enol tautomerism. On top of this, we have acid base on the keto-enol group, because these are basically conjugated with one another. We have acid base on the phenol, we have acid base on the other phenol, such that in the total, we have 21 different chemical states that we need to evaluate inside the pocket of three different structural models, one for the 6' PDB ID, and two chains in the case of the 5' models. So I will not show you the ligand residue interaction plots. We're going to go directly to the overall in-pocket metrics. Here we see depicted the deformation energy, the chemical state relative energy, interaction energy, and also the total in-pocket binding energy, which is what we are actually after. And if you look in detail in all of these plots, you'll see that chemical state 10 leads to the lowest in-pocket binding energy in all of these three different cases. In other words, the chemical state 10 is supposed to be the preferred chemical representation of curcumin inside DIRC2's pocket, irrespective of structural model. This is what we have for chemical state 10. The problem that we have is the algorithms that are used to add hydrogen atoms, they are not aware of the chemical environment in the protein. This means that even though we add the hydrogen atoms, they might not be in the position to lead to the best hydrogen bond network in the protein pocket. Therefore, we need to run a few additional calculations to basically try to optimize the interactions between the protein and the ligand. In the particular case of curcumin, we have a few questions. We start with the phenyl rings or the phenyl groups. Are the hydrogen atoms pointing downwards or upwards? The same happens to the other phenyl ring, or to the other phenyl group. Then we have the question, is the hydrogen atom in the keto-enol group pointing inwards or outwards? Is it in the left oxygen or in the right oxygen, or perhaps in the middle? In other words, we need to optimize the hydrogen bond network, which is what we show here for the case of the 6' model. So we start with what in-pocket gave us originally. You can see that the hydrogen atom here points downwards. This one is inwards, and this one also points downwards. So we can start by asking the question on the first phenyl ring, do we get an energetic gain if we basically put this hydrogen atom pointing upwards? In this case, we establish a hydrogen bond with a nearby glutamate 193. The in-pocket binding energy goes from -47 to -58. We have a significant gain, and therefore we take this change and proceed with a further evaluation. We go to the next phenyl ring. Is the proton better there, or shall we flip it upwards? If we flip it upwards, we'll see that there's going to be a clash with the nearby lysine 153. The protons are not represented here, but there will basically be a clash between the protons. We get rid of a hydrogen bond. This leads to a decrease in the binding energy. Therefore, we reject this change. Now we go to the keto-enol group. And in the case of the keto-enol group, we start by trying to flip the hydrogen atom outwards. if we flip, you immediately see a clash with the nearby leucine 231. We reject this change. We try to put the proton in between the two oxygen atoms, shift it to the left atom, and in this case, all these optimizations led to a proton closer to the left oxygen atom because it leads to a slight increase in the hydrogen bonds with glutamate 229. So in the end, we had the full in-pocket optimized representation of curcumin inside of DIRC2 for the 6-star model. Of course, we need to repeat the whole thing for the 5-star models. We're not going to do this in the interest of time, but what we have is then here the overall results represented in this plot. So we have here the 6-star, 5-star chain A, 5-star chain B. We see that the deformation energy and the relative isomeric state energy is more favorable for the case of the 6-star models. We can see that the relative energy of the tautomer, the chemical state 10, is slightly more favorable in the case of the 5-star chain A model. We can see the interaction with the environment is significantly more favorable in the case of the 5-star model. However, when we add all of these contributions, we basically get a preference for the 6-star model, which makes sense from a chemical viewpoint because we expect that kinase inhibition directly engages the kinase's hinge, and this is the only structural model that does so. Neither 5-star A nor 5-star B engage the kinase directly with the hinge, and this is basically a no-go. On top of this, since hydrogen atoms are ambiguous, we decided to go back to the classical crystallographic metrics, and we basically took the 6-star binding pose, or the binding pose of curcumin in the 6-star model. We put it inside the 5-star chain A, 5-star chain B. We re-refined the models, and we obtained models with significantly better metrics. So with this, I hope I was able to convince you that within pockets, you can compare different structural models and have at least an answer or suggestion of which might be the most likely model to represent the biological assembly that you are working with. Now, with these two examples out of our hands, we're going to focus on impact on downstream applications and a few short stories to further benchmark and showcase what we can do with this algorithm. And before we go much further, I would like to revisit what happened in the case of axitinib bound to BCR-ABL. In the motivation, we processed the protein ligand complex according to the suggestions deposited in the PDB. We realized that the enthalpy of binding was overly low or overly stabilized, or a very large value. This backpropagated to the relative entropy of binding. And we also saw later in the in-pocket analysis of the system that there were changes in the topology of the ligand inside the protein's pocket. So we can now reprocess the system according to what was suggested by in-pocket analysis. We recalculate the relative energetics. We obtain now a relative enthalpy of binding of minus 3 kcal per mole, and we back calculate the entropy change to be minus 5 calories Kelvin per mole, in significantly better agreement with what you would expect from an ITC experiment. In other words, quantum mechanics is still safe. It's potential in the interpretation of the structural model that be the problem, or that can contain errors. And in this case, I would like to call your attention that poor interpretation of a structural model, for whatever reason, not trying to point fingers, but for whatever reason, a poor interpretation can be as bad or even worse than no structural model at all, because no structural model means no guidance. Poor interpretation can mean that you go in the wrong direction. Now, another question I would like to tackle is, can we only deal with ligands? And the answer to that is, of course, no. With recent extensions, we can now basically analyze how a residue, an amino acid inside the protein structure, or a post-translationally modified amino acid, interacts with the surrounding residues. And in the case that we have here, we have a protein complex, 10 different chains, and in these chains there's basically a oxidized cysteine residue to the sulfonic acid variant. And in this case, we basically decide to analyze this post-translationally modified cysteine residue. And as you can see, we have an acid here, and we can ask the question whether is this cysteine in the acidic form, meaning you have a hydrogen atom here, which can also go onto the other oxygen atom, or is it basically deprotonated, and what's basically the answer for this kind of residue inside the protein's pocket. So with the new extensions that we have introduced in the code, You can basically run this sort of analysis for all the different chain models that you have in the PDB. And we can basically see that the answer, what is the favorite chemical state of the CST residue inside the protein, is going to depend on the chain, is going to depend on the chemical environment. Sometimes we have the protonated form with the hydrogen atom on oxygen atom number 2. Sometimes we may have the hydrogen atom on the other oxygen. Sometimes the cysteine or this sulfinic acid may be deprotonated and we have instead the sulfinate. So the answer, what is stabilized, is going to be dependent on the environment, and we can run the analysis and have such an answer. Additional things that we can do. A problem in drug discovery is kinase selectivity, because the ATP binding pockets of kinases are also similar. Therefore, there might be off-target effects that we want to hinder, that we want to minimize. In this case, we took the drug silmitassertib, which is now in clinical trials for inhibiting the CK2 alpha kinase. And this is because silmitassertib is a subnanomolar binder to CK2 alpha. However, expectedly, there's off-target effects. For instance, the GSK3 beta or DIRC1A, for which you have binding affinities of almost 40 nanomolar and almost 2 nanomolar. So we have differences of almost 1 order of magnitude of binding of silmitassertib to these 3 different kinases. And even though the pockets are so similar, we can ask the question, why? And in order to answer this, you already see that I basically represented all the residues in the vicinity of the ligand using generalized letter codes. These basically represent positional residues in the structures. And we can see that there's differences between, for instance, CK2 alpha that has here a leucine, and here we have the isoleucine. And in this case, I think we have in the same position a valine. And we can basically run then the in-pocket analysis on this generalized pocket representation, and we basically overlay all of the structural models, all of these analyses, to try to get some answers. And here we can basically split the protein-ligand interaction patterns over the 4 different regions. We start with what I call the no man's land. We have some ups and downs, but nothing really special happens there. Then we go to the catalytic lysine, a critical element in kinase inhibition, and we can see that the lysine engages the ligand over the carboxylate group, and we have a preference, a preferred interaction, a more favorable interaction in the case of CK2 alpha than in the case of GSK3 beta or DIRC1A. Then we have the hinge region, which is very, very interesting in this case, in my opinion, because we can see that we can basically play with different residues in order to shift potentially the selectivity towards CK2 alpha or GSK3 beta. And last but not least, we have the region of the selectivity histidine, that what I call the selectivity histidine. You can see that in the case of CK2 alpha, we have an energy stabilizing interaction of minus 4 kcal per mole. And in the case of the other 2 kinases, we have basically 0. We can go back to the structural models. The selectivity histidine is basically here. You can see in the CK2 alpha that we have a T-stack with the chlorophenyl ring of the silmitassertib molecule. In the case of GSK3 beta, we have a glutamine that turns towards on the opposite way of the ligand, therefore leading to no interaction. In the case of DIRC1A, we have a glutamate residue that also turns itself away from the ligand, therefore leading to no interaction. And this interaction with the histidine was something that was previously observed in other work to be something important for the binding of silmitassertib to CK2 alpha, and was basically identified as a potential element of selectivity that our analysis basically recovered. The question that we have is, these are calculations on retrospective data, on retrospective analysis. Are these meaningful because they are just meaningful, or are we trying to push things towards our interests? And again, we run overall in-pocket binding energy calculations. You can see on the purple curve the in-pocket binding energy that we get directly from the model, and they don't really correlate with the experimental affinities because, as mentioned before, there's no cooperativity effects. We have an extension of the code that includes the whole chemical environment, the whole structural environment for the protein ligand complex. In this case, we will introduce pocket cooperativity effects, and when we do so, we are basically able to recover the relative trends of affinities of silmitassertib in the 3 different kinase pockets. So we are somewhat qualitative and quantitative in our analysis and understanding why there's a preference for the drug to bind CK2 alpha. I hope with this, I was able then to convince you that in-pocket allows for chemical comparisons of different protein ligand complexes and to extract additional informations. Now, at this point, I think it's important to reanalyze philosophically the scientific value of good structural biology, because we have been analyzing protein ligand complexes like the one that you have represented here. They show different chemical environments. They show a very rich and broad chemistry that we can use to train machine learning models, learn the interactions, and devise better models to basically accelerate drug discovery. And this is a particular case that was very fascinating for me because as a chemist, I'm interested in the complex chemical situations. And here we had a pocket of where a ligand with this imidazole ring would go inside and basically interact with 4 different carboxylate groups from aspartate and glutamates, even though only 2 are represented here. But this was basically a very interesting test case for the algorithm, because chemically we would expect the ligand to be protonated, and the in-pocket analysis basically gave this result. And when you have such models, when you have such interpretation, such additional data augmentation, there is potential value for drug discovery, there is value for training AI, and we are definitely enriching and giving more information on the structural databases. The problem is, this is only good if the models actually exist. In the case of this model, when we introduce one hydrogen atom on the imidazole on this imidazole ring to basically get the imidazolium protonation state, we are basically, irrespective of the orientation, irrespective of conformation, generating clashes with the nearby residues. So we had in this case an unexpected situation where in-pocket was suggesting something, but this something was not good from a structural viewpoint because it would lead to clashes. So this work was developed in collaboration with CCP4. So we used CCP4 to go back to the re-refinement. We re-refined the structure, and when we re-refined the structure using the information also available on the paper, we realized that the density that you see here did not correspond to the small molecule represented in the PDB model that we have here. Instead, it corresponded to water, PEG, and zinc. And whereas one structural model has potential value for drug discovery, for science, even though it does not exist, the other one is completely useless because there is no added value for drug discovery. We cannot use these to train AI models, and we are definitely not enriching. We are actually misleading model development. So I know that the presentation focused a lot on kinase examples. Are these the only examples that we tackled? Well, the answer is no. Here is an overview of what we analyzed using in-pocket, several different protein ligand complexes, because chemistry is perhaps a bit more varied in the case of small molecule ligands. We also analyzed cryo-EM models, so size is not necessarily a problem for us. If we have several chains, as you can have in this structural model here, we can even try to extract some statistics and get additional information. We also analyzed protein nucleic acid structures and protein-protein interfaces, as you have here in the case of the proteasome. In all of these cases, there was always something to comment on, something suboptimal, sometimes an error of chemical accuracy, sometimes just a small inconsistency. At this point, I think it's important to talk about capabilities, availability, and efficiency. Let me start with the efficiency. Here we have a screenshot from my laptop where I'm going to basically run or start the calculation of in-pocket analysis. The calculation started. We determined here all the neighboring residues. We are now doing the quantum mechanical optimization of the ligand residue pairs. And within 25 seconds, this calculation is then going to be finished within my done in my computer. So you can see that the algorithm is very efficient and you can use it for large-scale applications. And yeah, here, successful calculation. What can you do with it? As already discussed, we use it mostly to analyze ligand, acid, base, and tautomerism, but you can also do the same for amino acids. You can use the algorithm to analyze whether an amino acid should be flipped. For instance, the asparagine, glutamine, or histidine residues may not be solved with good enough resolution, and therefore a flip might be possible. The algorithm basically checks such flips for you automatically. And we also have included a quantum mechanical clash score analysis that basically is driven by electronic density overlap. And you can see a representation here that will basically allow using this clash score analysis to tell you have a problem on axitinib, on the axitinib structure. In this position here, you have a clash between the hydrogen atoms, and you also have something suboptimal here near the tyrosine 253. As for availability, the code is going to be available as a standalone Python interface. It's already implemented into CRIMS from EMBL Grenoble. So if you use a high throughput crystallography facility, you can basically run ImPocket on the structure that you're solving and try to get a better chemical representation of the ligand inside the pocket. In the future, we're going to have CCP4, PDB redo, and PDB integration. If you're interested, you can just write me. You can check our bioarchive, which is for some time available online. And with this, I would like to go then for an overview. I hope I was able to convince you that ImPockets can give you a good description of a small molecule inside the pocket. Not just a small molecule, can also be an amino acid residue inside the protein structure. You can use these to determine chemistry or the chemical interface between elements in a protein, in a biomolecular structural model. You can use these to compare different structural models and answer the question, what is the best representation of a certain protein ligand complex? And because this is based on quantum mechanical analysis, you can also tackle complex environments, for instance, those including transition metals. And even if you don't want to use the method in the future, I hope I was able to convince you that a structure without the chemistry is still an incomplete model. So we need to go beyond just atomic coordinates. We need to get the chemistry in order to get better structural models. With this, I want to finish the presentation, thank people in my life. I want to start by thanking the guys from Helmholtz, in particular Federico. He joined the group to further develop the algorithm. I have a very big thank you to all of the CCP4 guys. John, Lucy, in particular Lucy, she was very patient working with us on the re-refinement of all the structural models, going back and forth, and we still go back and forth. So it's a real pleasure to work with the guys from York. Also Robbie and Garib, the guys from PDPE, of course, Samir and Jennifer. My friend Julian from Pfizer, who is basically trying to bring ImPockets to AI model development. And also a very, very big thank you to Hosan and his team, Sihan and Rafael, for all the interest in the tool, all the enthusiasm, and bringing ImPocket also into their frameworks. And with this, I would like to open the door and the room for questions in our